we've witnessed formication, crackling sound, and force, and now we have to pick one to think about. Well, this being a physics class, it has to be the force. So let's look at how to calculate the force. You do it with Coulomb's law. If I had to give Coulomb's law a definition, I would simply say it's the force between two charges. So let's imagine two charges on an axis, Q1, Q2, and think about the force between them. Now, force, of course, the electric force is a vector. And I know you're excited to think about it as a vector. I know you love vectors. But we're going to start just thinking about its magnitude. Just thinking about the quantity of force. So remember, a vector magnitude doesn't tell you about the direction. It doesn't tell you if it's positive or negative. It's just the magnitude. It's just the length of the vector. So we know it's a vector, but for now, let's just think about the magnitude. So this is equal to Ke, where Ke is Coulomb's constant. And it equals 9 times 10 to the 9 Newton meters squared per Coulomb squared. In some books, you might see a 1 over 4 pi epsilon naught here, where epsilon naught is the permittivity of free space. 1 over 4 pi epsilon naught equals Ke. It's just different ways to write the constant. So for Coulomb's law, it's much more convenient just to write Coulomb's constant, Ke. It also has an easy to remember value, 9 times 10 to the 9. If you're working in MKS units, which you should. Next, you multiply by the magnitude of each charge. So here if we have charge Q1 and Q2, since we're just doing a magnitude, here you would just put in a magnitude. Meaning, if it's negative, you don't worry about it. You just make it a positive number, whether it's positive or negative, because we're not thinking about the direction. And then in the bottom, we have the separation, which for now we'll just call R. And it goes as 1 over r squared. So that's your formula for the magnitude of the force. You can look at it and you get some intuitive feel for how this force behaves. You can see right away that it depends linear on each charge. Right? So by linear, I just mean that the charge is to the first power. So if you double Q1, you double the force. If you triple Q1, you triple the force. But it kind of is very sensitive to charge because it depends on each one linear. Right? So if you double both charges, times 2 would go up by 4. Okay? So it's a linear with charge, but there's two charges in there. It goes as the square, 1 over the square of the separation, which is kind of awkward to say. I once met a physicist, Knight, who would call it 1 upon r squared, which I think is a very classy way to put it. So the force goes as 1 upon r squared, which basically just means if the separation doubles, the force goes down by 4. If the separation triples, the force goes down by 9. So it's very sensitive to charge and to separation. We can also think about the direction. So this magnitude doesn't tell us the direction at all, but if we start to put actual charges in, or the polarity of the charges, plus and minus, then we can start to know which way the force goes. So without vectors, we just have to state it. When the charges are opposite, the force is attractive. So this would give you the magnitude, but you would have to rely on just this knowledge to get the direction. If the charge is the same, a positive charge here and a positive charge here, then the force is repulsive. And again, if it's the same, even if the charges are negative and it's the same, the force is repulsive. It ain't fiction, it's a natural fact. Now, I'm going to show you that this is true. So we're going to go back to our charged rod. So we don't have little spheres of charge, but we have objects that can be charged. So here's one. We know if we rub the rod with the cat fur, it comes out negative. And here I have a support holding a piece of Teflon tape and a piece of glass wool. So if you think back to your triboelectric series, you know that Teflon is way at the bottom. Teflon is always negative. And this is Teflon tape. It should also come out very negative. So I'm going to use the cat fur to charge up the tape, just like I charged up the rod, like that. And what we should see, they're both negative, so it should be repulsive. So we can make sure that we get the right answer, and sure enough, highly repulsive. Oops, sticks to the metal. There it goes. Can't even get them to touch, no matter how hard I try. Repulsive force between the two negative objects. Glass should be positive. I've rubbed it with some polyethylene bags, which left it positive. The rod is negative, so we can see, and sure enough, an attractive force, because that is the case of a positive charge and a negative charge. We can also use this demo to show that charge is conserved. When I rub, I'm actually transferring charge. We're not creating charge, we're transferring charge. So that means the fur should come out positive. Right? If the fur comes out positive, it should attract the tape. So let's check. It's not nearly as strong an effect because the fur doesn't hold the charge well. But there you go. You can clearly see the negative tape is attracted to the positive fur. Let's look at the magnitude again, and this time really calculate an actual force. So I'm going to do a problem that I found in the book. It's about something that Richard Feynman said. So Richard Feynman, a very famous physicist, won the Nobel Prize, crazy guy, everybody loves him. So Nobel laureate Richard Feynman once said that if two persons stood at arm's length from each other, and each person had 1% more electrons than protons, the force of repulsion between them would be enough to lift a weight equal to that of the entire Earth. So the point he was trying to make is that electrostatic forces can be very strong. You know, so that was the idea. But let's see if this is correct. Let's see if it's right. So let's see. It was two persons stood at arm's length. Arm's length. So arm's length I think of as our hands are touching, and if your arm is about 3/4 of a meter is what I measured. Let's say the two are 1.5 meters apart. Now, if you ask a physicist to draw a person, that's basically it right there. That would be a person. I'll go a little more detailed on you, because we're trying to make this very friendly and sort of advanced class. So I'll do it like that. There you go. There's two people at arm's length, 1.5 meters apart. Now we also have to make a few assumptions. We have to assume their mass, which can be a little sensitive. So 70 kilograms, we'll say each one is 70 kilograms. And from this, we now know enough to calculate the charge and the force that these two would experience. So let's see, how much charge? Let's do that part first. Now that we've done this a little bit, we might be able to sort of do it all in one step. First of all, it's going to depend on how much they weigh, or what their mass is, I should say, 70 kilograms. And then we're going to divide that by the mass of a nucleon, 1.7 times 10 to the minus 27. And that's in kilograms per nucleon. So that would give you the number of nucleons. But then, only half of those are useful in terms of charge, so it's 2 proton per nucleon. So we're basically just dividing that by 2 to really just get the number of protons. So there's your number of nucleons, and now each one will have a charge of 1.6 times 10 to the minus 19 coulombs. So if you multiplied all that out, you'd get coulombs, right? This would be the charge, the positive charge in a person, just their protons. But then the question he said, or what he said was, imagine that each person just has 1% more electrons than protons. So the excess charge we're building up is 0.01. Taking the total charge in a human, just taking 1% of it and saying that's an excess of electrons, not protons. So I'll slap a negative sign on there. Right? So if you go through all that in your calculator, you'll get minus 3.3 times 10 to the 7 coulombs. Again, that's a lot of charge. And it's comforting that's not that different from the Teflon rod. Right? The Teflon rod had 18 million coulombs. This is 33 million coulombs. But of course, it's a much bigger mass, but then again, it's only 1%. The numbers look about right. So 33 million coulombs is the excess charge. So now let's calculate the magnitude of the force using Coulomb's law, the magnitude part. So it's 9 times 10 to the 9 Newton meters squared per Coulomb squared, there's KE, times 3.3 minus 3.3 times 10 to the 7 coulombs times minus 3.3 times 10 to the 7 coulombs. So we're assuming the two people are identical. Each one has that charge. So that's Q1 and Q2. And then in the bottom, I said they're 1.5 meters apart. Squared. Okay. So you do all that, and you get 44 times 10 to the 23rd newtons. 44 times 10 to the 23rd newtons. So Feynman has made his point. That is a pretty big force. Okay, so if you just had 1% extra electrons, you couldn't go near anybody because you have such a big force. However, let's see if it really is effectively the force of the mass of the Earth. Now that whole question doesn't make sense because you need the Earth to generate the gravitational force. So let's not worry about that. Let's just set this equal to mg and see what is effectively the mass it would take to create this force. That's really what he meant. And you can see, g is more or less 10. So it's going to be roughly, the mass that we're calculating is going to be about 4.4 times 10 to the 23rd kilograms. So I just divided basically by 10, put the decimal point there. Well, the mass of the Earth is 6 times 10 to the 24 kilograms. So, I'll never get to say this again, Feynman was wrong. Right? It looks like it's actually not quite that big. Okay? However, I'm not allowed to conclude that Feynman was wrong. That obviously would be very unwise. So really, though, it depends on all these numbers. You can see formulas are often very sensitive to little parameters that you put in. For example, if we made them weigh a little bit more, that would be more charge. And you might say, well, maybe a little bit more, but it's squared. Right? So if we made them weigh 2 times more, it would be 4 times higher. Right? And also the separation is also squared, also very sensitive. Maybe when he said arm's length, he meant they were like, hugging. Because you make them twice as close, and then again, it goes up by 4. So it doesn't take much to get you from 4.4 to essentially, or 0.44 to 6. It just depends on really how you estimate the numbers. The point really is that it's a very, very large force. Electrostatic forces are very big, and coulombs are a lot of charge.